Hi there. So in today's lecture, I'd like to talk to you about the motion of charges in electric fields. So last lecture, we talked about electric fields and drawing electric field lines. And so today I'd like to talk about the implications of that. Remember that anytime you have a force caused by an agent, in this case, the force is caused by the electric field on a charge, and the equation for that is F equals to QE. But anytime you have a force, you can always set that equal to Newton's second law. That force will also equal to the mass times the acceleration of the object. So here we can say that the force, which is always defined as MA, is equal to QE. So that means that QE equals MA, okay? So Newton's second law, F equals MA, set that equal to the F equals QE from the electric field, all right? Now, if the QE force is the only force on the particle, okay, and you don't have to worry about the net force, then you can do this. F equals QE equals MA, okay? All right, now, if the electric field is uniform, now let's be honest here, most of the time it's not. Most of the time, you're going to have an electric field that decays off as you get further from the charge. So it's not going to be like a number like 1,000 or something. It's going to be some function, and it'll get smaller the further away you get from the source. But if you have that situation, and I'll show you when you have that situation in just a second, then you also have a constant acceleration because you have QE equals MA. So if E is a constant, Q is a constant, and M is a constant, that means A is a constant, okay? So under those very small sets of conditions, then you can have a use of the kinematics equations. Remember from last semester's physics that the kinematics equations are for constant acceleration situations. Okay, so that's when you can use that. Now, if the particle has a positive charge, then the acceleration is in the direction of the field. Why? Because mass is never negative. If the particle has a negative charge, then its acceleration is in the opposite direction to the field. Remember that that's because positive charges go in the direction that the electric field points, but negative charges want to go opposite or upstream to the electric fields, okay? Now, since the acceleration under these very small sets of circumstances is constant, then the kinematics equations can be used, and you have A solved for in your kinematics equations. So F equals QE is equal to MA is true if there's no forces other than QE, but E is not always constant. Usually it's not. But when it's not constant, of course, you can't use the kinematics equations to solve for the resulting motion of Q. So only when the field is constant can you do that. Now, when is the field constant? Well, here's one way to make a nice constant electric field. You have a parallel plate capacitor, okay? So when we say a constant electric field, we mean that the electric field stays the same strength and points in the same direction for some region of space. And the way to make that happen is to have, now envision this in 3D, you have a positively charged flat plate above a negatively charged flat plate, and those plates are parallel to one another. Under those circumstances, you're going to have an electric field that points straight from the positive plate to the negative plate in that region in between the plates. Now, as you get off between the center of the plates, your electric field is going to kind of bow out around, okay, and not be uniform there. But right in between the plates, especially close to the middle, you're going to have a nice straight uniform field that doesn't change magnitude. And this is parallel plate capacitor. And we'll talk more about capacitors later, but that's what we've got. Okay. Okay, let's do an example problem because example problems are king. Let's say that we have an electron in the middle of some capacitor plates, okay? So that it's got this nice uniform electric field. And we watch what the electron is doing. We can track its motion. And we can see that it increases its speed from 2 times 10 to the 7th meters per second to 4 times 10 to the 7th meters per second over a short distance of 1.2 centimeters. So what would our electric field strength be? Okay, well, if we have a uniform electric field, then we can use the kinematics equations, okay? Now, if you don't remember our kinematics equations, I'll put a link underneath the link to this lecture to some information on the kinematics equations for you. Okay, so you can go back and look at it. Also remember, you can read your textbook, and that kind of stuff was covered in the early chapters of Giancoli. Okay, so you can go back and look up the kinematics equations there. But basically, there's 3 or 4, depending on what book you look at, there's 3 or 4 kinematics equations for 1D motion. Now, since all we know here is that it's increasing its speed from 2 times 10 to the 7th meters per second to 4 times 10 to the 7th meters per second, and we're given the distance, but we're not given a time, then what we're going to have to do is use the kinematics equation, the only one that doesn't have time in it, right? Okay, so that equation is VF squared is equal to VI squared plus 2A delta X. Remember that? Okay, so we have our final velocity. In this case, VF is 4 times 10 to the 7th meters per second, right? We have our initial velocity. In this case, VI is 2 times 10 to the 7th meters per second. We have our delta X. That's 1.2 centimeters, okay? And so that means that we can solve for our acceleration. So VF squared is equal to VI squared plus 2A delta X. Plugging in 4 times 10 to the 7th meters per second squared is equal to 2 times 10 to the 7th meters per second squared plus 2A times 1.2 centimeters. You got to put that in SI units, so 0.012 meters, okay? Remember, you got to switch centimeters to meters. So that's our equation, okay? And so what we would then do is rearrange and say 4 times 10 to the 7th meters per second squared minus 2 times 10 to the 7th meters per second squared divided by 2 divided by 0.012. When we do that, we get our acceleration. And A here is 5 times 10 to the 15th meters per second squared, okay? That gives us our acceleration. Now, once we have our acceleration, we use our new friend, our equation F equals QE equals MA. Okay, if we rearrange that, we get A is equal to QE over M. Okay, so here we have A, which is 5 times 10 to the 15th meters per second squared, is equal to QE over M. Q in this case, it says it's an electron. In the covers of your textbook, you have constant sheets. Remember, in an earlier lecture, we said that the magnitude of the charge on the electron is 1.6 times 10 to the minus 19 coulombs. With more sig figs, it's 1.602 times 10 to the minus 19 coulombs. So I'm plugging that in for Q. The mass of an electron is 9.11 times 10 to the minus 31 kilograms. Again, that was covered in an earlier lecture, but it's also something, a given constant that appears in the covers of your textbook. So plugging in for Q and M and setting that equal, QE over M equal to A, we can solve for E. E would be equal to 5 times 10 to the 15th meters per second squared times 9.11 times 10 to the minus 31 kilograms divided by 1.602 times 10 to the minus 19 coulombs, okay? And that gives us 2.84 times 10 to the 5th newtons per coulomb. So that is our electric field, okay? So that gives us our electric field strength. There you go. So you can combine what you know about electric fields with the QE part, with F equals MA, the Newton's second law part. And then if you have a uniform field, use your kinematics equations, which were covered last semester, in order to predict the motion of charges in fields, all right? We're not going to have too much emphasis on this in Physics 1104, but I do want you to understand that that's a possible thing that one could do, okay? So now let's talk about the direction that things would go, okay? So, whoops, sorry, meant to click that. If you have an electron in the uniform electric field and it's increasing its speed from 2 to 4 over the distance of 1.2, then this is just conceptual because the problem didn't ask it really, but what you'd have to do is, since it's a negative charge, then the field has to point opposite to the direction of motion from the electron because the charge is negative. Okay, I hope that makes sense. Thanks so much, and I'll see you around.